Hey guys! Today we're going to look at our first section of 2D forces. So this is a little catch-all unit where it has 2D forces and some miscellaneous forces involved. But it's important that we talk about them immediately after talking about our first forces unit. So the first thing that we're going to talk about is equilibrium. Equilibrium in two dimensions. In this unit, we'll be analyzing objects that experience forces from multiple directions. Remember, when the net force acting on an object is zero, the object is considered balanced or also called in equilibrium. This means that the object is either sitting still or moving at a constant velocity. So the entire purpose of this small section is that we are going to calculate what is required to keep that object sitting still or not accelerating. So the figure to the right shows three forces being exerted on one object. We can use this diagram to determine if the net force is zero or if it has a value. We can move the vectors as long as we do not change the angle at which they occur or the length of the arrow. So we can rearrange these arrows to get the following picture. So it zoomed in a little bit so the arrows look like they're longer than they should be, but essentially all we had to do was come up, move A immediately downwards, and move C over in this area. So A goes up, B goes down and to the right, and C goes directly leftwards. And we have this final picture at the bottom. Since all of the vectors are drawn tip to tail and there are no gaps or extensions, this is considered a balanced force. So hypothetically, if the arrow for B had our point right here, and this was open space, that would be an unbalanced force. Or if our arrow for B extended and ended here instead of here, that would still be considered an unbalanced force because those vectors are not even with each other. Since they are even, this is considered in equilibrium or balanced. So here's our diagram. If we have vector A and B, we want to 1, draw them tip to tail, 2, draw the resultant arrow, which is the sum of the two vectors, and then 3, draw the equilibriant arrow. So A and B, not tip to tail, so we took B and shifted it over this way and added it here instead of here. So now we have A and B, and we drew our dotted line, which was our resultant. We've calculated that in the past. And then we took our resultant and mirror imaged it. All we did was flip the arrow at its tail. So we took this spot and flipped it completely opposite. So this is a diagram of what the equilibrium is. We find the resultant and we completely opposite it. That doesn't really make sense, but if we have a resultant that is north, that means the equilibrium is going to be south. So same number, directly opposite direction. So we're going to do a couple examples of doing this calculation. How can we solve for the equilibrium of this picture? Suppose you have two forces acting on an object. The sum of these forces is called the resultant. You should know that already. The force that puts the object in equilibrium is called the equilibriant, and the equilibrium is equal in magnitude and angle but opposite the direction. So if we look at this diagram, we are going to want to rearrange it slightly and make it tip to tail. So essentially we're going to take the 15 Newton force going upwards and move it over here. Then we want to solve for the resultant, which is the diagonal or the line that connects the beginning point to the ending tip. So if we solve for this red line, that is our resultant. All we have to do is change the direction of the vector to calculate the equilibriant. So if this arrow is 15 newtons and this arrow is 35, we solve for the red arrow by doing Pythagorean theorem. 35 squared plus 15 squared equals c squared. 35 squared is 1,225. 15 squared is 225. So we have 1450 equals c squared. And then we're going to square root that value and C is 38.1 newtons. So the value of this red line is 38.1 newtons. But we're not done yet because we do need the angle and the direction. So we're going to use inverse tangent, just like we have in the past, of the opposite, which is 15, over the adjacent, which is 35, and that equals theta. Inverse tangent of 0.428 equals theta, and theta equals 23.2 degrees. So we're starting at this line and traveling up to our resultant. So we are 23.2 degrees blank of blank. The 35 degrees goes west, and that's our second blank spot, and we are traveling north of west. So this is the length of that red line. Now what we have to do is reverse it and find the length of the equilibrant. So we're going to take everything we just found. The only difference is we are going to change these two letters. So the equilibrant is 38.1 newtons at 23.2 degrees. Instead of north, it's going to be south, and instead of west, it's going to be east. Okay, so the first steps we've already done before. The last step is just flip-flopping the directions. So a practice problem. An object has two forces exerted on it. A 25 Newton force due south and a 60 Newton force due west. What is the magnitude and direction of the equilibrant? So keyword equilibrant, not resultant. So we have to calculate the resultant and then flip-flop the directions. So the first thing I'm going to do is draw this. 25 newtons south, 60 newtons west. We're going to calculate this line, and then we're going to reverse it to find that line. So to solve for the green line, that's going to be our first step. We're going to use Pythagorean theorem. A squared plus b squared equals c squared. 25 squared plus 60 squared equals c squared. 625 plus 3600 equals c squared. C squared equals 4225, and c equals 65. Now we have to calculate the angle and direction. Inverse tangent of opposite over adjacent, so 60 over 25 equals theta. Inverse tangent of 2.4 equals theta. Theta equals 67.4 degrees, and we need our directions, so blank of blank, and the first leg that we drew is south, so that is our second blank spot, and we traveled west of south. So now I'm going to rewrite everything, we're just going to change the direction. 65 newtons at 67.4 degrees, and instead of west, we're going to be traveling east, and instead of south, we're going to be traveling north. So in class tomorrow, what we're going to be looking at is how to find direction, because that's one of the really confusing parts, and practicing solving the resultant and then switching to the equilibrant. So I will see you guys tomorrow.